the last little thing I'm going to add in before you start, I suggest, your homework. Start your homework, work through problems that we've done up till now to really solidify what we've done, solidify your understanding, is this thing called the reaction quotient. So at the end of today, you should understand what it is, how it's similar to K, and what it tells us. So if Q is bigger than K or less than K, what does that tell us about how the reaction is going relative to equilibrium? So Q and K have the exact same equation. So the same way you write a K equation, an equilibrium equation, you can write, or you will write, Q. And Q is just the reaction quotient. So it is a capital Q, not a little q like for heat. It is a capital Q. And it essentially is going to tell us, well, I'm sorry, let me back up. You're going to use the amounts that you currently have only because you don't know if those amounts are equilibrium or not. That's the purpose of it. So unlike K, where we're using that value when we know we're at equilibrium, Q, we can use amounts at any time and compare the value of Q to K to figure out what direction what direction the reaction needs to go in order to get to equilibrium. So if Q is a lot bigger than K, then that tells us that the reaction is going to be going towards the products. Towards the reactants. So we have a lot more product than we have reactant, so it is going to go towards the left. And if Q is less than K, sorry about that, Q is less than K, then that just tells us we haven't reached equilibrium yet. Everything is still progressing to the right. And if Q, should have mentioned this one, if Q equals K, then we know we are at equilibrium. Then Q is K. So let's take a look at this. I have nitrogen gas and a hydrogen gas. We're going to make ammonia. We know what our Kc is. And you know what your molar concentrations are for each of these compounds. So which way will the reaction go to get to equilibrium if I know that I'm starting off with 0 ammonia? Is it going to go to the right, to the left? It's at equilibrium, or you can't tell. Oops. Sorry about that. Means if I have started off with nothing of my product, then of course it's got to go to the right, right? Otherwise you have nothing happening in your beaker, you have no reaction. So if you're starting off with nothing of something, then you know it's definitely got to be going in that direction. So in this case it would be going towards ammonia. We haven't made any yet. Okay, so same thing. Now I have 1 molar of N2, 3 molar of hydrogen gas, and 2 molar of ammonia. So which direction do you think this is going to go? It's going to go to the right, to the left? Can't tell. What do you think? Okay. So this is kind of a trick, because if you noticed, the molarities match the stoichiometric coefficients. What we're going to do on the next screen is figure out how would we determine that. There we go. So this is the exact same quantities. Now, my K expression, what would that look like? That's K is going to equal my ammonia squared divided by my N2 and my hydrogen gas cubed. So Q is going to equal exactly that, right? And we know what our value is. We have our equilibrium constant value is 0.5. So what do we have here? Q is going to equal my NH3, which is 2.00 squared. So remember, we're going to use Q to figure out if we're at equilibrium yet. So 2 squared divided by my N2 and my H2 concentrations, So my N2 is 1.00 times my H2, which is 3.00, and that is cubed. So what do we get? 4 divided by 27. It's definitely going to be smaller than that. Yes, my calculator told me it's 4 divided by 27. That's not helpful. So 0.148. So Q is less than K. So we are going to the right is how the reaction is still progressing. Tells me we haven't reached equilibrium yet. So when I come back to this equation, to the initial question, then the trick here is you cannot let the quantities of the molarities trick you into thinking that you've reached equilibrium because they match your stoichiometric coefficients. It's a trap that people fall into all of the time. You've got to actually go through this step where you just do some quick math and see how your Q compares to your K, and that will tell you what the true picture is for your equilibrium projection. So if I am progressing to the right, because my Q is smaller than K, what side of the Rice table would you put a minus X on? So remember, our Rice table was two videos ago. Which side do you think the minus X would go on? Would it go on the left, right, both, or can't tell? Hopefully you came up with the left, right? Because the equation is progressing to the right. So if it's progressing to the right, then that means the quantity of my products, my reactants are decreasing. Hopefully that makes sense. If I'm going to continue going to the right, I have to continue using the stuff that's on the left. So my minus X is going to go on the left. Okay, so I have these quantities. I have 1 mole of Br2, 1 mole of H2, and 1 mole of HBr added to a 1 liter vessel. Which side of the Rice table would you put the minus X on? Kc equals 0.20. Okay, so let's take a look. I have Kc equals, let's see, I have 1 mole of everything, right? I have 1 mole of HBr, 1 mole of this, 1 mole of this, and 1 mole of this. So let's just write our Kc equation. So I'll have HBr squared divided by Br2 and H2. And we have values. This is 1 mole of each per liter, so everything is 1. It's 1 molar for each. So I'll have 1 squared divided by 1 times 1, which is otherwise known as 1. Okay, so this, actually, that's my Kc, and I should be very, very careful here. Sorry, my hand is forgetting which one is which. That is my Kc, but what I just put in there was actually my Q, because we don't know if that is at equilibrium or not. So this is Q. Okay, so Q is, let's see, 1 is definitely greater than 2, or 0.2, sorry, is greater than K. So that means I am progressing to the left instead of the right. So if I'm progressing, if my reaction is going to the left rather than to the right, where am I going to put my minus X? On the right. So whichever direction your equation is going, the side the arrow is pointing away from, that's the side that's decreasing. So in this case, my HBr would be decreasing. So I'm going to be a minus 2x here, and this would become a plus x because that's the direction it's going. So that's the benefit of doing our Q calculation, is letting us figure out, so we can use our rice tables to actually determine what these quantities are. So let's see how that looks. Let's give that a go. So I have my ice table then, if we're using the same mole, so we had 1 mole of everything. Okay, come on, computer. If you recall, everything was 1 molar. So this was 1 molar, this was 1 molar, and this was 1 molar. So this is going to be my initial concentration. It's probably the easier way to think about that. So let's just kind of do this. Remind ourselves, this is my reaction. My initial concentration, I guess I could have just done it there, is going to be 1, 1, 1. Okay. My change, let's see, this is plus x, this is plus x, and this is minus 2x. So what do I get here when I put it all together? Then I get my Kc equals, it's the same thing, my products over my reactants. So my HBr squared divided by my Br2 times my H2. And when we put in our values, what do we have? We have 1 minus 2x, that quantity squared, divided by x times x. And that equals Kc. So this is just like the other one that we had, because this is going to simplify down into 1 minus 2x squared divided by x squared. And remember, the trick that I showed you before is, oh dear, I'm glad I made that mistake, because you get sucked into forgetting. Yeah, bad juju. What did I do wrong here? I skipped a step and then convinced myself that I was starting with 0 when I'm not. This is my equilibrium concentration is 1 plus x and 1 plus x and 1 minus 2x. That's what happens when you skip steps. So Kc then is, that still holds, 1 minus 2x squared divided by 1 plus x times 1 plus x, otherwise known as 1 minus 2x squared divided by 1 plus x squared. So the same trick applies here that applied to what we did when we first looked at rice tables. And that trick says, if I take the square root of both sides, I make that ugly square go away, and I don't have polynomials everywhere. So I'm not going to end up doing a quadratic equation. So I have the square root of Kc is going to equal 1 minus 2x divided by 1 plus x, or Kc, or the square root of Kc times 1 plus x equals 1 minus 2x. Remember, the name of the game is to get x all by itself. So I'll have the square root of Kc plus x times the square root of Kc equals 1 minus 2x. So we want to get the x's on one side and everything else on the other. So square root of Kc, actually, what do I want to do? I'm going to do the other way. Move this over here. I'm going to get rid of that minus 2x and make it positive. So I'll have x root Kc plus 2x equals 1 minus the square root of Kc. So let's just double check, because I did a bunch of stuff in my head. So this is positive. I moved the minus 2x over to the left. And then on the right, the 1 was positive. It stayed. And I subtracted the square root of Kc. Good. And then the same thing, I can factor out x. I get the square root of Kc plus 2 equals 1 minus the square root of Kc. And then finally, we're ready to put numbers into our calculators and be error-free, hopefully, divided by the square root of Kc plus 2. So let's see what we get. 1 minus the square root of 0.2, and the square root of 0.2 plus 2. So 1 minus, I'm expecting this to be a pretty small number. Like that. 0.225. Oh, okay. Okay. Whew. 1 molar. 0.22588. All right, we have 3 sig figs, I think, on everything. So it'll be out to 3 sig figs is my x. So I'm going to end up with 1.25 or 1.226 and 1.226 and 1 minus. So at equilibrium, we'll have 1 minus 2 times this. So my equilibrium concentration here is going to be 0.548. So let's check it out. So that means, drum roll please, Kc is going to equal 0.2258 quantity squared divided by, oops, nope, I put it in the wrong spot. Sorry about that. My HBr is the 0.548. Let's erase that. Erase. Yep. So my HBr is the 0.548. 48 squared. And my x, 1 plus x, is 1 point that, 1.2258 squared. They're both the exact same concentration. So let's see, what do we get? This guy squared divided by 1 plus this, and that quantity squared. Hallelujah. Push the button right this time. 0.20. So checks correctly. I got all excited. Now I can't even write the number 2. 0.20. There you have it. So we used our rice table. And notice that I wrote my equilibrium constant the exact same way I did every other time, even though I knew that the equilibrium was favoring to the left, right? So the only thing that changed here was that I knew that my HBr was going to be decreasing in concentration, so it ended up with a minus x, whereas the original reactants ended up increasing in concentration. So keep that in mind. We use our Q, figure out which direction things are going to go, and then when we use our ice tables, we use that information to determine where the positives and negative signs go on our rice tables. Sorry about that.